Structural Analysis to Chapter 8 Deflection Using Energy Methods. If we do have a cylindrical rod hanging from a fixed support at the top, and a load of axial load of N is applied at its free end, we want to calculate the strain energy due to axial force. So in that case, we do know the strain energy is area under force displacement. So if we draw the force displacement, area under force displacement, which is equal to a half of P force times delta or N, can replace P with N here, and that's a half of P times delta. And the logic for that is the external work done will be converted into internal strain energy that is sorted in the bar. So this much of area show the internal energy due to a work of external load like N or P, which is applied to the free end of our bar. So if a half of N times delta, which is the area under P delta diagram, which is the area of this triangle we talked about, that's the internal energy. It's stored in the bar as internal energy, and at the same time, from mechanics of solids, we do know delta, the formation due to a force, is NL over EA. If we combine these two equations with each other, it just says internal energy is N squared times length of our bar over 2E times area. Considering this equation for internal energy stored in our structure, and let's see how we can calculate the effect of deflection with the stored energy. So now this time let's consider a cantilever beam handling distributed load of W over the span of beam with a length of L. We want to know likewise we want to know what is the internal load due to bending, and that's likewise that's the integration from 0 to L. That means all over the cross section of beam. M squared this time, that for axial load we do have N squared L over EA, and that's UI due to axial load, axial force. And this is the same concept, but forget about integration because that's a distributed load. We need to add them all up together, so that's a summation or integration. And this time do bending, m squared this times dx. If you integrate it over the span of length, that turns to m squared L over 2 E times I. Just be careful about the axial stiffness and something like a bending. So if we want to apply the principle of work and energy, for example, cantilever beam, fixed support at A, and the concentrated load at the end, like you can see here, point concentrated load of P is applied. It will no external work is converted to internal strain energy, and we want to solve the unknown of delta by equalizing these two terms, external and internal, and calculate the delta from that. So if we just cut our section through by a length of x, can easily do a summation of moment about x goes 0. That gives us a negative mx due to all arbitrary direction minus p times x, which is again a clockwise, goes 0, and it just gives us mx is equal to negative p times x. And likewise, if we just replace and use internal g is m squared L over 2 which is integration over equation of moment. As soon as we have the equation, we can replace it there and integrate it, and it just gives us over the length of, which is length of L, it just gives us a 1/6 of p squared L cubed over EI. And if you remember the load of the work of external, which is the effect of P is a half of P times delta energy, the delta curve again. We talk about that. That's the area under this triangle. So it just gives us a half of P times delta. And if that's equal to a 1/6 of P squared L cubed I, the only unknown here is delta. And it just simply gives us the amount of deflection, which is PL cubed over I. Just calculate the amount of deflection, like what happened here in terms of deflection of real beam. Any method you can get like L cubed over PEI. You can use drawing method from mechanics of solid for creating the shear and moment, then theta and then delta drawing method, or moment area method, or integration method itself. It just gives you an energy method. It just gives you a direct answer for this question. So that's a kind of singular approach to calculate the delta maximum at the free end. So now let's go a bit deeper to a principle of virtual work. One can call that a work and energy method, like a real load. And the second, this is what we have talked about so far. We can call that the real load because we are working with the real. But principle of virtual work, which is developed by a John Bernoulli, a Swiss mathematician born in the mid 17th century and died in late 18th century, and is one of the famous scientists, mathematician from the Bernoulli family. He developed the principle of virtual work in 1717, and it just called also like a unit load method. We'll talk about it in a few seconds. So principle of virtual work, it just says if we want to calculate the displacement in terms of translation or rotation, if something is moving, just a angle of theta is rotation, can easily get that like by applying one virtual load at that location, and then times delta is equal to summation of all internal forces. So by a 1 unit of virtual load, we can calculate a real displacement. That's the benefit of principle of virtual work, which is gives us a better hand on a calculation of deflection, because all the time we don't have the force at any location of our structure which we want to calculate the displacement. So for example, if I want to calculate deflection at any of these 3 points, I can easily do that with the real work method, which is work and energy. But if I want to calculate it here, calculate the deflection here, the displacement at point A, for example, because there is no real force here, I cannot do that because I just can calculate the displacement where I have load in work and energy. If I just by the help of virtual work, I apply a one, for example, unit of virtual loading, I can calculate the real delta at any location, and that's equal to summation of internal energy. For rotation, it's just 1 unit of moment times theta. It's a summation of u theta times delta f. Talk about them in detail. So it just says for a principle of virtual work, if we have our structure which handles the real loads of P3, P2, and P1 at some point on the structure, and if we just want to calculate delta at somewhere, for example, point A is here, we cannot calculate the displacement at point A by the help of real load method because we need a load to calculate. So for example, you can easily calculate deflection here, and also displacement here, but not at point A with the help of real loads. So if we just apply a virtual load of 1 unit like P prime at point A, we can calculate, or any other point, because point A is an arbitrary point, can easily calculate the deflection or displacement at any point of our structure. And that's the strength of using a virtual work approach. Again, summation of forces times delta work of external load is equal to summation of work of internal loads. We talk more detail about the virtual work and solve some problems in next videos. Thank you.